Now that we have reviewed basic concepts of precalculus and algebra needed for our course, we can begin to learn about a truly new concept that will link precalculus to calculus. Section 1.5 is about limits, mathematical limits, not speed limit, safety limits, or any other kind of limits. In this section, we will learn what a limit is and how we notate limits. Then we will see how to estimate a limit numerically and graphically. We'll also see ways in which a limit can fail to exist. In the videos for the other half of this section, we'll get more rigorous and see how to determine limits algebraically. Then we'll summarize all of the methods for finding limits. The limit is a concept that is fundamental to the study of calculus. You'll have to wait a little bit longer to see why limits are so important for us. Here's a comparison to give you a sense of what the difference is. In precalculus and algebra, you often take a static view of a function. In other words, you often answer the question, what is the y value at a particular x value? In calculus, we begin to take a more dynamic view. We'll answer the question, how are the y values behaving as we change the x values? A mathematical limit is a tool that we use to describe this behavior. What is a function's outputs doing as the input values become closer and closer and closer and closer to some particular number? Let's take a look at an example. Here is a graph of the function f of x equals x cubed minus 1 divided by x minus 1. It looks pretty normal, except there's a hole or a gap at x equals 1. Why is there a gap there? Well, if we try to plug in x equals 1 into the function, in other words, if we take a look at what happens at f of 1, and we substitute a 1 in for x, we're going to get a 0 up in the numerator and a 0 down in the denominator. And any time that we have a 0 in the denominator, this means that we have an undefined value. If we take a look at the function and remember all the things that we've been learning about with domain, we can see that x equals 1 is actually not in the domain of this function. Every other number is okay, because if we look at the denominator here, x equals 1 is the only thing that's going to cause us a problem, which is why we only see a gap at x equals 1. Now, you might kind of give up and say, well, we can't plug a 1 into the function, so we don't know what's going on there. But the graph can tell us a different story. We want to be able to know what's happening as we get closer to 1, and maybe that'll tell us a little more information about that hole or that gap. So with a limit, when we can't plug in a number into a function, what we do is we try to figure out what we might expect to happen there if the hole wasn't around. How will we do that? Well, we will examine what is happening near, in this case, x equals 1. One way to do this is to make a numerical chart. We often set up a table like this to organize the information. Let's plug in some values. You should be using a handheld calculator for this course. Here on the right-hand side, I've just got an approximation of what kind of calculator you might have, a TI-84 or TI-83. Here's an easy way that you can use your calculator to plug in some values. If we put the function into y1, so if you hit y equals on the upper left corner, we'll carefully put in our equation. So we've got a bunch of stuff in the numerator, so we've got to put parentheses around that. We will put in x to the third, then minus 1, close parentheses, and then that's divided by, and yours will look a little different. This is just a cheap, free iPad calculator. Then we'll divide by parentheses x minus 1. Now, if we hit the graph button here, we can see that this function does look like a parabola. And yours again might be a little bit different. Yours probably won't show this gap or this hole like this online calculator that I have does. Oftentimes the gaps are a little exaggerated in our pictures because we want to make sure that we understand that there is a hole there. But really that hole is very, very tiny. You wouldn't even be able to see it. So when you graph this in your calculator, it won't look like there's a hole at x equals 1. We have to be smarter than that and understand that there is a hole there. So we're not going to use the graph to use this shortcut, but if you do have your function in y equals, there are a couple options that you can do in order to make a shortcut of plugging in these x values. Now, if you want to just go to the home screen and substitute in each of these x values, that's totally fine. Sometimes people feel like that they make some mistakes doing that, so here's, again, just a shortcut. You can go to Table Set, which is the second from the top left above Window. So you'll go Shift and then Table Set. And normally the independent is on auto, but if you hit ask instead, then we can go to the table and we can just type in the X value that we want to plug in, and it will spit out the Y value. So if you go again to table set, which is above window with the shift button, and change independent to ask and hit enter. Then if we go to table, which is shift graph, table above the graph button, if you have it on ask, then this should be empty. So if we tell it what X value that we want to plug in, which is 0.75, and hit enter, it gives us the Y value out. So it's 2.3125. So let's organize this in our table, 2.3125. And then we'll keep on going. We'll plug in 0.9. I type in 0.9, hit enter, we get 2.71. Okay, we'll plug in 0.99. We're getting closer to 1, but from the left with numbers that are smaller than 1. When we plug in 0.99, we get 2.9701. And then lastly, we'll get even closer to 1. We'll plug in 0.999, which is pretty close. We get 2.997. And these might go out a little further on a more powerful calculator than this cheap one here. Yours might have more decimal points, but you can kind of round to 3 or 4. That would be good. So we can see here that as x approaches 1 from the left-hand side, as we're getting closer and closer to 1, but from this direction, we want to see what's the behavior of the outputs. What are the y values doing as we look from left to right, as we're getting closer to x equals 1? Are they approaching anything? And if so, that's what the limit's going to be. So we can see here that these are getting like pretty close to 3. In fact, we could even get closer to 1. We could do 0.9999. And I know it doesn't ask us for this, but let's just do that in the calculator. And we can see it, the y value is 2.9997. So that's even closer to 3. So this table here tells us that our f of x values approach 3 from the left-hand side. Now we can also let x approach 1, but from the other direction, or from the right-hand side on the number line. So we'll start with something that's a little bit bigger than 1, like 1.25. So if we substitute that into our table, we get a y value of 3.8125. We can do better though. We can get closer to 1. We can plug in 1.1. That's a little bit bigger than 1, but closer to 1. And if we substitute, no, I'm not a student. If we substitute that into the table here, we get a y value of 3.31. Okay, we can do even better. We can get closer to 1. So 1.01 would be a little bit bigger than 1, but closer than 1.1. So we'll substitute that in for x. Okay, this comes out to be 3.0301. And we can do even better. We can do 1.001. That's closer to 1, but a little bit bigger than 1. And we plug that in, we get 3.003. Now we could keep going. We could do 1.0001, 1.00001, and we could get closer and closer to 1, but there'd be no ending to this. We could get as close as we want. What we're trying to do is see, is there some kind of behavior happening with the y values that we can kind of tell just by plugging in maybe 4 or 5 values in for x. So we can see here that this trend, or the behavior of the y values, again, these are getting closer and closer to 3. These numbers are bigger than 3, whereas from the left, these numbers were smaller than 3, but they are getting closer to or approaching 3. So from the right-hand side, we would say that f of x also approaches 3. Here's a second way that you can plug in some x values into a function, a shortcut using your calculator. If you have the function in y equals, you can go back to the home screen and you can ask it to plug in x values here. So if you hit the vars button, which is below the up, down, left, right arrow key here, so it says vars, if you hit that, and then you hit enter on functions, which should be your first option, it brings you to a list of y1, y2, y3, etc. Wherever your equation is plugged into, which mine is in y1, so I'm going to hit enter on y1. Oop, you got to be on the home screen. So there we go. It should put that on the home screen here. And to substitute in an x value, in parentheses, you're going to plug in the x value that you want to substitute in. So let's just start with 0.75. Close the parentheses, hit enter, and it tells you what that y value would be. And you can keep on doing this instead of using the table if you prefer. So we'll go to vars again, hit enter twice to substitute in y1, and then in parentheses we could put in 0.9 to plug in x equals 0.9. And there it is, 2.71. Alternatively, if you are using Desmos, which you can do, but again, you should be using a calculator for this class that you can hold in your hand, that is not, reliant on the internet. So if you plug in our function here, y equals x to the third minus 1 divided by x minus 1, here again we get a nice graph of its parabola, and you can see here that we don't really see a hole at the point that we can't plug in a 1 into. It looks very, very connected, even if we zoom in pretty far. But again, we should know that it is not. There is a hole there. You can ask Desmos to give you a table of values. If you hit this gear option, and this might be different on an actual computer instead of in iOS system, and you click this thing that looks like a chart or a table here or an Excel thing, then it gives you a list of values. You can change the x value to anything that you want. So if we type in 0.75 and hit enter, it gives us 2.3125. If we hit 0.9 and hit enter, then it gives us 2.71. If we substitute a 1 in, it's saying that it's undefined. So it's actually finding these values correctly, even though, again, on the graph, it looks very connected. So back to our example here. The idea is that even though the graph has a gap or a hole at the point where x equals 1 and y value would be 3 at that hole or gap, so the coordinate of that hole would be 1 comma 3, with the limit we can move x infinitely close to 1. Like even though we only plugged in 4 values here, there's a lot of numbers in between 0.999 and 1, and we could sit here and just plug in infinitely many numbers in between 0.999 and 1 and get closer and closer to a y value of 3. We don't have to do that if we just kind of see the pattern here, and we will learn more rigorous methods for us to evaluate limits where we don't have to take a guess. Again, this idea will be true all the time. So as a result, f of x will move arbitrarily close, or as close as we want, or closer and closer and closer to the value of 3. So shifting back to looking at what the graph of this function looks like, remember it was a parabola and it had this gap here at x equals 1 because we can't plug in 1. We did find though that the limit was 3, meaning that as you approach x equals 1 on the curve, we're looking at what the y values are doing. And we saw that as you approach x equals 1 from the right-hand side with numbers bigger than 1, we got numbers that were bigger than 3 for y, but they were getting closer and closer to 3. We also saw that as we approached x equals 1 from the left-hand side, that the values of y were getting closer to 3, but with numbers that were less than 3. But they were pinching towards this y value of 3. So if we didn't know any better about what happened at x equals 1, we would probably assume that the y value would be 3 there. Again, if we just kind of didn't have this information about what happened there. So this idea can be sort of summarized in this sentence here. Although x cannot equal 1, again, we can move arbitrarily close to 1 or as close as we want. And as we do this, f of x moves arbitrarily or as close as we want to 3. Now that's a lot of words. We like in mathematics to summarize stuff into nice, neat little package notation. In this case, we will use what is called limit notation to summarize this. Limit notation is a condensed way, again, of describing this relationship. What we write is LIM for limit. Underneath the LIM, we write what x is heading towards. In this case, x is approaching 1. So we write x and then an arrow to 1. The function here is what comes next after the lim. Now, normally we'll see the actual equation or the actual formula for f of x. So maybe in this case, We could say the limit as x approaches 1, and our function was x to the third minus 1 divided by x minus 1. And that will be equal to 3. What your limit is equal to is what you find the y values are approaching. So as x approaches 1, the y values are approaching 3. So we would read this as the limit of f of x as x approaches 1 is 3. Or you can say as x approaches 1, f of x approaches 3. So generalizing this to any x value, not just 1, and any function, if we have a situation where the y value of a function, f of x, becomes arbitrarily close to a single value L as x gets closer and closer and closer to a number c, on both the left and the right-hand side, then what we say is the limit of f of x as x approaches c is L. So we have to understand what this means. This thing that is highlighted in green is saying exactly the same thing as this big long phrase up here. And this thing that's highlighted in green is saying the exact same thing as what is in this nice little packaged condensed notation. We have to understand that the function here, again, will be the specific function we're looking at. This c here is what x is approaching, and this L here is what the y values are approaching. Again, we can read this as the limit of f of x as x approaches c is L, or as x approaches c, f of x approaches L. We could also write this in like two separate pieces. We could say that f of x approaches L, y values approach L, as x approaches c. So you want to think of this arrow here as sort of meaning approaching or heading towards, as opposed to being equal to. We will probably stick with this notation more, but you might see this in other situations.